Okay, so we're going to look at one of the, I suppose, primary kind of questions or things that we use within probability here, which is a specific type of experiment or kind of probability experiment that we can calculate the probability of, and it's called a Bernoulli trial. Okay, it's used to calculate the probability of a certain number of successes within a certain number of trials, irrespective of when those successes occur. So we'd be looking for questions like find the probability that they hit the target twice in their 5 shots. Okay, doesn't matter where in those 5 shots these two successes happen, so long as there are only two. Okay, there are a number of criteria or characteristics that have to be met for something to be considered a Bernoulli trial, and I suppose it is important that you know all of these and that you're familiar with all of these characteristics. First one, there has to be a fixed number of trials, so obviously it can't go on forever. Naturally enough, we can't compute a probability that continues indefinitely. The end trials must be independent. Okay, so because they're independent, we're multiplying the probabilities. We're saying 8 successes and 2 failures in 10 shots. So we need independence there to be able to multiply the probabilities. They must also be repeated under identical conditions. So the probability is not allowed to change in any way. There may be only 2 outcomes. Okay, now how we kind of work around that one sometimes can be looking at one outcome as success and then anything else as failure, but we have to be able to basically describe it in 2 kind of distinct ways. And leading on to the next one with that idea as well that those are the only 2 outcomes, and that the probabilities then of success and failure will add to give me 1, of course, because they are the only 2 options. And then again, the probabilities must be constant for all trials. A lot of this kind of logically makes sense. We can't do this calculation if the probabilities have a chance of changing as we move through the number of trials here. Okay, what we use then in working out these probabilities is the binomial distribution here, okay, which models the number of successes in a fixed number of Bernoulli trials. It gives the probability of k successes in n trials, okay, so the probability of succeeding k times in n attempts. And the probability of that is n choose k, because we want to choose that number of successes here. So we're looking at combinations. How many different ways can that happen? We go with the probability of success to the power of k and the probability of failure q to the power of n minus k. Okay, and linking the two in that way then. N is the number of trials, k is the number of successes, p is the probability of success, q is the probability of failure, and then as we said, the n choose k is the number of ways I could choose these successes from all of the trials that I've taken here. So let's look at an example or 2 of some of these. An unbiased die is thrown 5 times. Find the probability of obtaining 1/6. Okay, so the probability of obtaining 1/6 out of the 5, well, we need to just set up some examples here. So P is the probability of success, which is the probability of getting a 6. So that's a 1 in 6 chance. Q is the probability of failure, which is not a 6. So a 5 in 6 chance. So even though obviously there are 5 other options, we're only considering it as either I get a 6 or I don't. So the probability there that I get 1/6 in the 5 throws. Well, out of the 5 throws, I'm choosing to succeed in 1. I want a 1 in 6 chance, so that's going to happen once, and then the 5 in 6 is going to happen 5 times. And I can calculate that then with my calculator here. So let's just set this up. 5 choose 1, 1 over 6 to the power of 1, 5 over 6 to the power of 5. And we get an answer of 0. Let me see, sorry, to the power of 4, of course, to add up to 5, as we had here with our binomial distribution originally also, and we get 3125 over 7776. Part 2, 3 6s, so out of the 5 we want to choose to succeed 3 times, which means I need to fail twice. Okay, making sure, as I missed out on the first time there, that my 2 powers add up to match up to the number of trials in the question there. So if I succeed 3 times, I then fail 2 times. Okay, so we'll just adjust my formula here. So this is power of 3, and then, oh, typical enough, all things changing on me. Okay, there we go. 5 over 6 then to the power of 2, and we get 125 over 3, 8, 8, 8. and looking then of the probability of at least 1/6. So to calculate at least 1/6, we just have to have a small little think about what that means. So the probability of at least 1/6 means we cannot have the probability of no sixes. So the probability of at least 1/6 is the same as 1 minus the probability of no sixes. Because if I remove the option of having no sixes, then I'm ensuring that every other possibility will have no sixes, or will have at least 1/6. Okay, it's kind of a complement rule here. So we're basically saying that taking away the probability of no sixes removes the only case where we end up kind of not satisfying our question here. So what we need to look for then is the probability that I get no sixes. So out of the 5 trials, I want to succeed never. 1 over 6 is to the power of 0. You can kind of see what's happening here. And 5 over 6 to the power of 5. 5 choose 0 is just 1. Okay, lovely. 1 over 6 to the power of 0 is just 1. So really, the question just ends up being 5 over 6 to the power of 5, which does make sense, because if that's the probability that I get no sixes and no sixes and no sixes 5 times, which would just be that probability multiplied by itself, since it is independent. So we get 3125 over 7776. So the probability of then at least 1 is 1 minus that, which is 4651 over 7776. Okay, that idea of at least 1 is a common enough sort of question for them to use here. So definitely one to just kind of consider and make sure that you're happy with, even beyond your Bernoulli trials. So we'll look at example 2. For this example, I'm just taking an exam question, so feel free maybe to even give this one a go for yourself before we kind of work through it here. But 2017, question 1, Connor rings Kira's house. The probability that Kira answers the phone is 1/5. Connor rings Kira's house once every day for 7 days. Find the probability she will answer the phone on the 2nd, 4th, and 6th days, but not on the other days. So that's a very specific outcome. So we're not being told here that we want her to answer 3 times. We're quite specifically told it's the 2nd, 4th, and 6th days. Now, the fact that it's those 3 days isn't really going to affect the probability. Like, really here we're being asked the probability that she answers 3 times, but just one case of that. So what I would do is I would try and list this out. So we're basically saying we want her to not answer. We then want her to answer, then not answer on the 3rd day, answer on the 4th day, not answer on the 5th day, answer on the 6th day, and then not answer on the 7th day. So the probability she does answer is 1/5. So the probability that she answers is 1/5, which means the probability that she does not answer is 4/5. Okay, and instead of NA, we could use like our A complement there instead. So the opposite of A. So we're basically saying we want 4/5 times 1/5 times 4/5 times 1/5 times 4/5 times 1/5 times 4/5. Okay, and simplifying that down here, we're going to end up with 4/5, which is the probability she doesn't answer on 4 of the days, and 1/5, which is the probability she does answer on 3 of the days. So you should maybe recognize here that this is very, very similar in layout to a Bernoulli trial, but the only thing that's missing is the choose or the combination at the start here. And the reason we're not including that is we're not looking for the probability that she answers 3 times across the week and look at every possible way that could happen. We are looking at one distinct version where she answers 3 times. Okay, so that's going to give me 256 over 78125. So quite a small probability there. Find the probability that you will answer the phone for the 4th time on the 7th day. Okay, this is a very, very typical sort of question, so it's one we'll dwell on a little bit here. So if she's going to answer for the 4th time on the 7th day, we just need to consider what that means. We need her to answer 3 times in the first 6, and then look at the probability she answers, where this last one is for the 7th day. So we're basically saying here we need to answer 3 times in those first 6 days, wherever that may be, because all of these are potential options. We need to look at all the options where she answers 3 times in those 6 days, but then we also need her to answer on the 7th day. Okay, so that would be a case of probably she answers on all of those days and answers on the 7th day. Okay, so let's have a look at that. So this Bernoulli trial for the first one, out of the 6 days, we're choosing that she answers on 3 and doesn't answer on 3. And then we also want her to answer on the last day. So we multiply by another 1/5. The multiplication there again lining up with our use of the word and here and the fact that they're independent events. So we know if events are independent, we multiply our probabilities. So that's essentially going to give me 256 over 15625. So again, even as probably slightly slightly more likely than the previous answer that we had, that she just answers in that one specific occasion. So let's look at the next part. Connor rings her house once every day for n days. Write in terms of n the probability that Kira will answer the phone at least once. So this is one of those at least questions again. So the probability of at least once. The only outcome we don't want to consider is the probability that she never answers. Okay, and the probability that she never answers is going to be that she doesn't answer, which was 4 out of 5, for the 7 days of the week, or for the n days, excuse me, because this is n days now. So that's the probability that she never answers, 4 over 5 to the power of n. The probability then that she answers at least once will be 1 minus that to the power of n. Continuing into the next part of the question here, we're told to find the minimum value for which the probability she will answer at least once is greater than 99%. So we're being told here the probability that she answers at least once needs to be greater than 0.99. So we've already worked out that this is 1 over 4 over 5 to the power of n, and we need this to be greater than 0.99. So let's do a little bit of work here. I'm going to kind of swap sides a little bit. So 0.01 is equal to 4 over 5 to the power of n. Okay, so 4 over 5 to the power of n is less than 0.01. We need to convert this now to a log equation. So what we might do is look at the value of n, which would give me 0.01, and then consider what we would need to look at with n then to give me a value less than 0.01. So converting to log form, okay, and we've gotten it a bit backwards here, but this is my base, okay, my power, and then my answer part here. So this is going to be log to the base 4 over 5, 0.01 equals n, which means that n is 4 over 5 to 0.01, so n is 20.637. Okay, we need to consider here now, does n need to be greater than or less than this 20.637? Okay, the idea here is that if n is smaller, okay, if n is smaller than this, well, we can try it out. So let's try 4 over 5 to the power of 20, for example, and we get 0.011529, which is not small enough. Okay, that's not equal to 0.01. It's in fact larger than 0.01. Reminder that we want this expression to be less than 0.01. So we're going to have to round upwards. Okay, so we're going to have to say that n is greater than 20.637. So the minimum value will have to be 21. So if we use a minimum of 21 days, then the probability that you will answer at least once will be greater than 99%. Okay, it's quite a few days though. Okay, we have to do at least 21 days to be sure that she'll answer at least once with a 99% certainty, or more than 99% certainty. Okay, so let's get into some of these exam questions then to do with Bernoulli trials. I think we only have a few here to look at. Yeah, 4 maybe to look at. And again, we're going to see a lot of the same things across these exam questions here. So the first one, a certain basketball player scores 60% of the free throw shots she attempts. During a particular game, she gets 6 free throws. What assumptions must be made in order to regard this as a sequence of Bernoulli trials? Okay, so we mentioned a lot of these earlier, so we'll kind of quickly fly through even a few that we could mention here. One assumption that would have to be the case is that the probability does not change. Another would be that the probabilities are independent, okay, or that the trials are independent. We need to have only success and failure. We need to have a finite number of shots. Okay, and again, there's some more. I think we've kind of covered a lot of the things there. The probability of success and failure must add up to 1. Okay, so there must only be those 2 options, and then they must add up to give us 1. But yeah, we've hit a lot of kind of the points there. And again, as I say, these were the things we talked about at the start, those characteristics of a Bernoulli trial. So based on these assumptions, find correct to 3 decimal places the probability that she scores on exactly 4 of the 6 shots. So we're not told a specific 4 here, we just want the probability that she gets 4 out of 6. That's a Bernoulli trial. So out of the 6 shots, we choose to succeed on 4 of the shots. The probability she does succeed is 60%, which is, I suppose we'll use 0.6 here maybe. So she's going to get 4 of them. And then the probability she fails then is 0.4. And that's going to happen twice on 2 of the shots. So let's calculate that value there. So 6, choose 4, 0.6 to the power of 4, 0.4 to the power of 2. Oh, sorry, kept typing there. 0.4 squared, and that's 0.31104. We're told to 3 decimal places, so 0.311. So about 30% chance that she scores 4 out of the 6 shots, which seems reasonable based on her kind of rate of success there. She scores for the 2nd time on the 5th shot. So when they specify a particular time that we're looking for, we just need to take that moment to just write out what that means for the scenario here. So to score for her 2nd time on the 5th shot, she needs to score once in 4 shots and score. So we need 5 shots in total. Of the first 4, she scores once, then we want her to score again on the last one. So for the first 4 shots, it's a Bernoulli trial. Out of the 4, we only want to succeed once. So that's 0.6 to the power of 1, 0.4 to the power of 3. Because we're using the word and there, as we said already, that relates to multiplication because they're independent events. The probability she scores on that 5th shot, it's an isolated independent event, kind of unaffected is the word I'm looking for by what has come before. So the probability she scores on that one is just 0.6 on its own. And I can adjust what we have here a little bit. So 4, choose 1, 0.6 to the power of 1, 0.2 to the power of, or 0.4 to the power of 3, and then times that by another 0.6, 0.09216. And we were told 3 decimal places, so that's 0.092. So about a 9% chance that that occurs. Okay, let's keep moving. People with O negative blood type are called universal donors because their blood can be given to anyone else. In Ireland, approximately 8% of the population have O negative blood. At a blood donation clinic, 10 blood donors give blood one after the other. Find the probability that the 10th person is the 3rd O negative donor. Okay, again, let's list out what that would mean. So we want 2 O neg in 9 and O negative, okay, which gives me 10 total. So with the first 9, I need 2 O negative donors, and then I need the 3rd person to come as I need the 3rd donor to be the 10th person who comes to me. The probability of success here is the probability I get O negative, which is 0.08. Failure then is 0.92, so quite large here. So out of the first 9 times, I want to only succeed twice. So 0.08 to the power of 2, 0.98 to the power of 7, and we want O negative on the last one, which is another 0.08 then for the last case there. That's going to give me an answer of, let's see, 9, choose 2, 0.08 squared, 0.98 power of 7 times 0.08, and that gives you 0.016. 4 decimal places, 0.0. Let me see, sorry, I think I've typed in something incorrectly here. 0.092, excuse me. I mistyped my probability of failure here. So let's adjust that one. There we go. Perfect. That seems a bit better. I was kind of thinking 4 decimal places, but we didn't really have 4 decimals of value, of significant value here. So 0.010, and it's 28, so we'll write that to 3. So we're looking at about 1% chance that that occurs, okay? And given that the chance of getting an O negative donor is only 8%, 1%, yeah, seems kind of reasonable there. At a blood donation clinic, 5 donors give blood. What is the probability that at least one of the 5 donates O negative? So the probability that at least one, okay, we've done this kind of sum nearly 3 times here at this point. At least one is the probability, 1 minus the probability of none. The probability of none, we don't even have to treat as a Bernoulli trial because we're just looking at getting none. 0 plus 0 and 0 and 0 and 0 and 0 of the 5 donors. They're independent events, so 0.92 to the power of 5 for that one. And that gives me 0.659081. So 1 minus that is going to give me an answer of 0.3409. Find the minimum number of blood donors required so that the probability that at least one of them is O negative is greater than 0.97. Okay, so again, we're looking for the probability that none out of a sample of an unknown size, which is 0.92 to the power of n, okay, because we don't know how many it is. The probability then of at least one of n is 1 minus 0.92 to the power of n. We want this probability to be greater than 0.97. So very similar now to the one that we were just looking at as our example here, 0.92 to the power of n. Let's look at the case here where this is equal to 0.03. So writing it in log form, 0.92, 0.03 equals n. That gives me an n value of 0.92, 0.03, 42.054. Okay, now we know that that value that I need, so they're basically saying here to get a value of 0.03, I need to be slightly over 42, which means the minimum value of n is 43. So to be sure that I would get a probability of one of them being O negative greater than 97%, I would need to have at least 43 people. Okay, which again, given a probability of 8%, seems fairly reasonable there, really. Okay, let's keep moving forward. The Road Safety Authority has data on driving test pass rates at all of its test centres. In a particular driving test centre, the probability that a person taking the test for the first time will pass is 1 over 4. All of the test results are independent. In this centre on a particular day, Joe, along with 5 others, takes the test. All 6 are taking the test for the first time. Find the probability that Joe passes the test along with exactly 2 others. Okay, so let's kind of break this one down a little bit more. So the probability of passing is a quarter. All are independent. Joe, along with 5 others, take the test, so there's 6 of them altogether. We want Joe to pass and 2 others to pass. So we want the probability of Joe and 2 out of 5. So we're basically saying Joe, well, the probability he passes is just a quarter, and, so multiply, Out of the 5, I want 2. A quarter to the power of 2. 3/4 then is going to be the probability of failure, and that's going to be to the power of 3 here. And that gives me an answer of 135 over 2048. Okay, so a low enough probability there, I suppose, on average there. The overall pass rate for all drivers at another centre is a half, whether it's their first or subsequent attempt. On a particular day, n people take the test. The probability that 2 people or less than 2 people pass can be written in this form. So that's interesting here. It's 2 people or less than 2 people. Find the value of A, B, and C. So we're basically considering here the probability that it's 2 people or 1 people or 0 people. And we should hopefully remember that the word or means addition. Okay, the word or to us kind of says addition here. So let's look at this. The probability that 2 people pass, okay, the probability that 2 people pass out of n people is n choose 2, a half to the power of 2, and then a half to the power of n minus 2. Okay. Simplifying that then, n choose 2, because both of these have a base of a half, we can apply our indice rules here, which would tell us to add the powers. So that would be 2 plus n minus 2, which just gives me a power of n here. Okay, so it kind of works for us here that given a half, 50%, a kind of 50-50 chance, kind of works for us here basically in terms of the probabilities. The probability of 1 is n choose 1, a half to the power of 1, and then a half to the power of n minus 1. So we actually end up with the same situation here, where it's n choose 1, but a half to the power of n. And again, we're going to end up with the same thing here in the next one. A half to the power of 0, and then a half to the power of n. So again, n choose 0, a half to the power of n. Okay, we're going to be adding all of these. Now we can do a little bit of work on some of these ones here. N choose 0, we should hopefully remember, and you can try it out with any number. 6 choose 0 is 1, n choose 0 is always 1. So 1 times a half to the power of n. Okay, over here next, we'll keep our half to the power of n. N choose 1 is always going to be n. How many different ways can I choose one thing out of n things? N different ways. The one to really look at is going to be the n choose 2 here. Okay, the n choose 2 is probably the most awkward of the three to consider. Okay, and in order to look at it, we need to look at our factorial rules. Okay, so going back to that work you would have looked at, and you can go kind of look back at that one. But n choose 2 is n factorial over 2 factorial times n minus 2 factorial. And remembering that difference between, say, n choose 2 and the permutation there, and how it affects the factorials as well. That addition of the 2 factorial, we're kind of removing the choice there, or the difference of repeating options. We can do a little bit of work with this one. N factorial is n times n minus 1 times n minus 2 times n minus 3, which I can write as n minus 2 factorial. 2 factorial and n minus 2 factorial on the bottom. I can then cancel the n minus 2 factorial to get n squared minus n over 2 factorial, which is just 2. Okay, so this is my n choose 2 here. Okay, this is my n choose 2 here, having been rewritten. So to express that then in our question here, it becomes n squared minus n over 2 times a half to the power of n. Okay, we have a common factor here of a half to the power of n. So let's see what's left behind. N squared minus n over 2 plus n plus 1. Okay, continuing onwards here. A half to the power of n, n squared minus n plus 2n plus 2 all over 2. And we get a half to the power of n times n squared plus n plus 2 all over 2. Okay, Nearly there now. Okay, we're close to the format that they're looking for. I do note that the format on the bottom is 2 to the power of n plus 1, and what I have at the moment seems to just be 2 to the power of 1. So maybe there's something I can do with the half to the power of n. Well, applying my indice rules would say that can be 1 to the power of n over 2 to the power of n. 1 to the power of anything just stays at 1, so it becomes 2 to the power of n. So multiplying this now by the other bracket that we have will give me n squared plus n plus 2 times 1, and then 2 to the power of 1 times 2 to the power of n, so 2 to the power of n plus 1. And we've shown or identified that expression there. A, B, and C, the coefficients of my quadratic here. A is 1, B is 1, C is 2. Okay, making sure I answer the question as well by identifying those coefficients there. Okay, slightly tricky question there, without a doubt. Okay, definitely requiring a good grasp and understanding of your factorial rules there and your combination rules. Okay, we'll continue onwards. In a particular population, 15% of the people are left-footed. A soccer team of 11 players, including one goalkeeper, is picked at random from the population. Find the probability that there is exactly one left-footed player on the team and give your answer correct at 3 decimal places. Okay, so let's have a look. The probability of success, if we can think of success here as being left-footed, is 15%. There are 11 players on the team, including one goalkeeper. And these are picked at random. Find the probability there's one left-footed player. So out of the 11 players, I want to succeed only once. 0.15 to the power of 1 and then 0.85 to the power of 10 gives me an answer of 0.325. Probability less than 3 players are left-footed. Well, that would mean 2, 1, or 0. Okay, we already know 1. So out of 11, choose 2. 0.15 to the power of 2, 0.85 to the power of 9 here. We already know that this one is 0.325 from the first part. And over here, out of the 11 people, I want to choose 0. 0.15 is to the power of 0. And in fairness, we could leave that out altogether and just look at the 11 at the end. That's going to give me 0.287 plus 0.325 plus 0.167. Sorry, I'm conscious that I'm running on a bit longer than I intended, so I'm just going to kind of take some of these answers for myself here. 0.779, 2 decimal places, 0.78. The goalkeeper is left-footed. Find the probability that at least 8 of the remainder of the team are left-footed. At least 8 are right-footed. Okay, they're trying to catch us out here, are right-footed. Well, that's going to be the probability at least 8, so 8, 9, and 10. Okay, the probability of left-footed was 0.15, so right-footed is 0.85. So out of the 10 people remaining, we want to choose 8 of them being right-footed, so 0.85 to the power of 8, 0.15 to the power of 2, plus out of the 10 people, we'll choose 9 of them to be right-footed, 0.85 to the power of 9, 0.15, and out of the 10 people, we'll choose all of them to be right-footed, so that's 0.85 to the power of 10, and 0.15 to the power of 0. And that's going to give me an overall answer of 0.82. Okay, as my answer for the probability that at least 8 are right-footed. Okay, that's basically our Bernoulli trials. You can see there's loads of different types of questions and things involved in there. The main thing really for you to note is going to be those rules as to what makes it a Bernoulli trial, and then just refamiliarizing yourself a little bit with that idea of a binomial distribution, that idea of the n choose k, and even as you saw there, having that understanding and that grasp of working with your combination notation is going to be particularly important also.